Well, thank you all for coming to our first Nature at Noon series. So Nature at Noon is a series of lunchtime presentations that we're having here at the Biomimicry Center, which we're inviting biologists to come and talk about their area of expertise and potential applications in biomimicry. So I'm Heidi Fisher. I'm the Assistant Director here at the Biomimicry Center, and I'd like to welcome you first in our inaugural series of lunchtime chats about biology. I would like to introduce Gita Bodner, who is an arachnologist from Tucson. I got to know Gita a couple months ago. We, along with a group of women scientists, had visited Aravaipa Canyon, and the place that we were staying had this incredible orchard around it. And the first thing that Gita did was put her luggage down and beeline for a pomegranate tree and break open the fruit. And immediately she recognized that there was a jumping spider that had made a little nest in the fruit. And this was like, what are the chances? That was just sort of the beginning of a whole series of amazing stories about spiders during our stay. For anyone who was at all squeamish about spiders, by the end of it, Gita's stories had just made us fall in love with spiders and just built our fascination and respect for these amazing critters. So Gita has a degree in anthropology from Harvard and then a PhD from the University of Arizona, where she did her dissertation on jumping spiders, probably the spiders that are most likable and for which people develop incredible affection. So she's now an ecologist for the Nature Conservancy in Tucson. So she'll give about a 20-minute presentation, and then she brought some live spiders with her that we can have some fun looking at under the microscope. So please welcome Gita Bodner.
Thanks. This is fun. I will say, so in my current life, I am not actively working with spiders, so it's a treat for me to get to go back to the spider world for a little while. I am working with an organization that does do some work in the realm of biomimicry, more or less, but more on the side of ecosystem-based natural solutions and promoting the use of nature-based solutions to ecological problems. So if you want to know more about that side of the work, there's this great blog called Cool Green Science, and blog.nature.org, and you can find out some of what Nature Conservancy is doing on nature-based solutions, harnessing them for major ecological problems, things like oyster reef restoration for mitigating, reducing damage from storms in ways that are both less expensive and more beneficial than some of the hard infrastructure, or that combine well with hard infrastructure. So that's the sum total 1 minute of my current life. And now I get to go on to spiders and how cool they are. And it's going to be kind of a whirlwind tour through 400 million years of spider evolution. There are about 114 families of spiders currently described. About 45,000 species described, but estimates are up to twice that many or more in actuality living in the world. One estimate recently came out that half of the species that are even in collections, that are pickled in museum drawers, half of the species in collections are currently undescribed. So that means that in terms of species in the world, there's a huge amount to be known just about the diversity, and then from there, all of the fascinating, crazy things that are embedded in that diversity of life, the behaviors, the materials, the craziness. So with that, and I put that on there to remind me to tell you guys that a bunch of the photographs in here are from this wonderful book, Amazing Arachnids. It's done by my friend Jillian, who took most of the photographs in it. So if you see a picture up there that's uncredited, it's probably hers. She is also a really good example of how a lot of the current discoveries and recent discoveries, some of the coolest discoveries in biology, are being made by artists and by people who are outside the sort of strict field. She got into spiders because she was an avid photographer, and then her interest mushroomed from there. And she's since discovered a whole bunch of cool behaviors because she is, as a photographer, she's paying attention and she's finding things that the rest of us didn't take the time to notice. So that's both a plug for her, a recognition of her photographs in here, and an encouragement that discovery is open to all, and that artists have a track record of generating some of the most interesting discoveries, and design folks too. We'll see that. So, all right. So, 400 million years. Where do we get that? We get it from a phylogenetic tree. Who here has had any experience with family trees of plants and animals and critters? A little bit, yeah. So I passed some around. There's a few of these sort of floating around. This is a stand-in. This is a reminder to encourage people to play with, go out, explore, see what you find. But then there's other realms of exploration, other realms that you can play in, and there is an immense amount of literature out now on how we think these critters are related to each other. And that's a whole other realm that we have open to us to play with and to try to understand. You find a spider, in a jar on the table, or under your patio furniture, or out on a hike, and that spider represents, in this case, 400 million years of evolution in a spider form, and in such, it's a window to evolutionary history. When you pick one up and let it jump between your fingers, you are interacting both with the spider in its current form, but also with its entire evolutionary past. And that evolutionary past has as many secrets as the current critter. And I'll get into a couple of examples of that from a sort of a potential sort of food for biomimicry ideas. So, all right. So, spider family tree as we think it exists. People debate about this. It's an active field of science to figure out exactly who is related to who. And as we come up with new hypotheses, they sometimes they have different implications for how we think things like orb webs evolved. But I'm going to go with this for right now. Okay. So, what do all spiders have in common? They all have in common venom. They all make silk and have these little structures called spinnerets that they use to weave the silk with. And they all have really kind of weird, cool sperm transfer organs on the male pedipalps. And you guys can see some of those later. So there are a few spiders that have lost their venom. There are none that have lost the silk, and none that have lost the very important things, how to make a web and how to make more of yourself, have been conserved in spiders overall. So, all right, that's what all spiders have in common. 100 million years down the road of being spiders came aerial capture webs. So the big wheels that we associate with spiders, and then I'll show some more examples of in a minute. Also, along with those new sort of aerial capture webs came evolution of new types of silk, and these cool pincher-type jaws. So who here has played with a tarantula? Yeah, they're cool, huh? So tarantulas are in this old lineage of spiders. The ones sort of pre-orb web or pre-aerial web. And they've got jaws that hinge up and down like that. Has anybody tried to cut a piece of yarn with a knife? It's really, really hard. Cutting a piece of yarn with scissors, totally workable, really easy. So tarantula guys have this whole set of spiders have up and down jaws. They have to actually have something to pin their prey against to get their fangs into it, right? So pretty much that means they're constrained to living on solid surfaces. So until the advent of these pincher-style jaws, think of scissors in the yarn instead of knife in the yarn. Until the advent of these pincher-style jaws, basically anything out in the air was not accessible to spiders. So when these pincher-type jaws evolved, it opened up a huge new world for spiders. 3 dimensions. It was 2 dimensions before, now it's 3. Now they can be just about anywhere. 100 million years later, again, approximately, spiders then, a whole big lineage of spiders left the web completely, left their capture webs behind, their aerial capture webs behind, and instead went out into the world to chase down, ambush, and hunt things on their own generally without much assistance from a web. They still use silk for a whole variety of functions. And there are some of these guys in this group here that's much bigger than it looks on this tree. There are a bunch that have actually sort of re-evolved some use of webbing to help them catch stuff, which is also kind of weird and cool. But mostly, okay, so ambushing and chasing things, right, 180 million years ago, that sort of diversity starts. And then that leads inevitably to the coolest spiders out there, jumping spiders, that are in this, chase down and capture group, the hunting group, active hunting group. And they evolve this whole new set of tools that help them succeed at chasing down and pouncing on stuff. So I'll show you guys in a little bit some examples of jumping spiders and how their hydraulically powered leaping legs and their advanced optics have opened up more dimensions for them, daytime dimensions for them. So, and they're my favorites. So, so I get to talk more about my favorites than about anybody else. So, all right. Questions, thoughts so far on 400 million years?
Yeah, where are crab spiders in that?
Crab spiders are right here. They're in the ambush and not using a web for prey capture. They use their silk for lots of other stuff, for getting from place to place, and for wrapping up their eggs and keeping them safe and all of that. But yeah, so they're in this hunting snag group.
And the black widow?
Black widows are, where are you? They are in this aerial web weaving group where there it is, right here. So they're right off there. And if you got this in front of you, you can scribble on it, and yeah, there it is. And there's actually, so that brings up, so they do these sort of disorganized, they look disorganized stuff. They're not a perfect wheel web. There's actually a lot of debate active in the field as to whether all of these guys from this group onward, whether they all come from a wheel weaving ancestor and many of them have lost the wheel weaving, or whether wheel weaving has evolved a bunch of times. And it's actually kind of hard to it's hard to tell which would be harder, right? So yeah, they are right there. With the yeah. Yeah.
What's your opinion on that debate you just brought up?
My opinion on the debate, I think it's actually a little more likely that the wheel weaving evolved once, maybe twice. I can't imagine wheel weaving evolving more than, well, twice as a stretch. But I actually, there's a whole sort of, there's a whole anthropology actually about how people imagine the changing of complexity, and for a long time it was, if you look through the history of science, for a long time there was almost no hypothesis that say that complexity was lost. And lots of hypotheses about how it's sort of imagining that we're all sort of aspiring to this great, perfect future, right? It's sort of a very directed view of evolution. Once, and I don't know when you would say that this changed, but at some point people started actually imagining that complexity itself is not necessarily it's not necessarily an inexorable draw, right? That in fact, simple can be better. And as soon as people started allowing themselves to think that simpler might actually have advantages, then we started getting all of these hypotheses about why it might be that that something that had like achieved the pinnacle of greatness might then devolve into simpler structures. So I think that's the more likely that we've had one really fancy web and then selection for simpler variations on that don't require as much energy or don't require as much, that can be done if you've lost a leg. It's really hard to build a perfect web if you've lost a leg. It's really easy to build a tangle web if you've lost a leg. So more flexibility in the world sometimes with simpler structures. Is that, yeah. Probably lost. But it's fun that the debate continues. Yeah.
Just a comment on what you just said. It's interesting because there's psychology research showing that if you give people something and say make it better, the way that they do is they always add more.
Right.
And you see this with the students, right? So you make it better, then they add another paragraph. When actually you can often make it better by having taken things out. That is the psychology of it that we have.
Right, yeah. So in a way, then we can do sort of biomimicry of psychology by saying by introducing examples of how other creatures have come up with simpler designs that function better. So yeah, that's fun. All right, and there's a huge amount of diversity and intrigue embedded within all of those guys. So, all right, so up here, venom. Venom is, so I'm going to go through a few different characteristics, a few different sort of suites of things that spiders have figured out really interesting and complex stuff with, and just give a couple examples of them, and then we'll start looking at spiders and having conversations, and the interaction is great. So let's continue that. So I'm gonna mostly punt on the question of how cool venom is. Venom is super, super, super cool. There's a huge amount of research now going into pharmacological uses of venoms. How can we use pieces of spider venoms and snake venoms and scorpion venoms in medical treatments? There's a lot of research going on into how we can maybe take components of spider venoms and use them for insecticides. And these guys are 400 million years of evolving chemicals that subdue prey, mostly arthropod prey. There's a lot in there. I'm going to gloss over it partly because the world of venom research is so big, and partly because we would spend the rest of the day on that, and it's not stuff you can see usually. So I wanted to bring one example from the cool venom world of stuff that we actually can see, and that is this guy named Cytodes, a spitting spider. These guys live around here. They might be in a wood pile. They're actually closely related to brown recluses and that group that have venom that they call medically significant. It poses a threat to us in a way, which is rare in the spider world. Not very many have medically significant venom for humans. Cytodes, spitting spiders. They get the award as most resembling superheroes. You see this huge, the big domed So this is the carapace, they call it, the head part, head thorax part of the carapace, and then the abdomen. Cytodes have this big swollen head, basically. Venom glands live in the head. This guy has sort of devoted a huge amount of space to storing extra venom because its way of catching things like little crickets that wander around is to spit glue at them and peg them down to the surface. It's who here remembers Gulliver's Travels? Yeah, that's Gulliver waking up strapped to the ground. That's what that cricket experiences when a spitting spider spits glue at him. So she lifts her. You can see her fangs right there. They're tiny little fangs. They would have a really hard time puncturing very much. But she has a lot of mobility in them. She can swing them forward, and then high pressure, she spits glue, and it goes in a zigzag. And there are actually people who have succeeded at videotaping this. So at some point, if you want, we could partner on putting together a set of little videos on the crazy things that some of these creatures do. She spits glue and pegs things down to the surface, and she can do it from like 3 or 4 inches away. So by the time she approaches that cricket, it's completely immobilized, that cricket, or another spider, maybe something more dangerous than a cricket, totally immobilized, helpless, and she can just go and then feed on it at leisure without any risk to herself. But her venom would have no real impact on us. It's been screened for some of since she's closely related to recluses. Folks have looked at spitting spider venom to see if they have some of the same compounds that are sphingomyelinase D. It's a compound that chops up muscle tissue, and they don't have it. So, yeah. Safe for us and very cool. And they actually sometimes live in some of the same environments as recluse head spiders do. So if you have these around, you're really, really happy that you have the superheroes that are harmless to us, and that they're probably actually displacing or eating some of the recluse types.
I'll just quickly share from a biomimetic perspective. For one of our clients that is interested in novel ways for nozzles, we shared this one with them to think about in a more passive kind of way, how could you ensure that you have the greatest dispersal area, but not in a 3-dimensional space, which our spray models are all, but in a more of a 2-dimensional space that we can more ensure more breadth than height in the spraying. So as you think about these stories, that's how you want to think biomimically, is who might care, who has that same functional need.
And then you get to asking, well, how do they do it? And then you want the high-speed videography and the detailed morphologic.
Exactly. And that's what we end up providing. We get into the diagrams and draw out all the pieces so that that can then inform the designers to figure out how to emulate that.
And I'll bet a lot of the spider biologists, the critter biologists, would be really interested in that too, because you guys might see things that they hadn't seen. They might still be wondering, well, how do they do this? And you guys would have figured out, well, here's how we would do it if we were doing it in some other way and do the spider sheets. Yeah.
Does the glue last a while?
That's a really good question.
Like, I wonder if there's
that
that cricket on my floor and I feel like I'm going to scrape it off.
That's a good idea. I have no idea, and I don't know if anybody's ever looked at that. It obviously lasts long enough. I'll bet it would last at least a couple days, because that's probably how long she takes to eat it. But which brings up a really other interesting question: is sort of once you make substances, how do you unmake them? Right? How long do they last? What happens after they're made? Which comes into play with capture webs. The question of how things are unmade is just as interesting as how they're made, and capture webs provide some examples of it. So, all right, so on here you remember, venom and spinnerets and fancy sex organs up here. Capture webs 100 million years later, 300 million years ago. It should be no surprise that in 300 million years we've got an immense diversity of web styles And those translate into an immense diversity of sort of functional attributes as well. So this is the sort of classic Charlotte's web. There are a number of other sort of wheel-like webs, and then there's a ton of other webs of other forms, like the tangle web weavers, and I'll show you a picture of some of how they do it. But you might imagine that in any of these webs, there's a bunch of different functions going on. Those translate also to a lot of different kinds of silk. Any given spider is likely to have 3 or 4 different kinds of spinnerets, and to be able to spin up to 7 different kinds of silk. So so the frame silk of an orb web is going to be a stiff silk, strong, stiff silk. There's some the radii are also going to be pretty strong and pretty stiff. But the spiral parts are you don't actually, if you're trying to catch stuff, you don't necessarily want something that's so stiff that things either bounce off of it, or if they're big and heavy and coming fast, that they punch right through it. You actually want something ideally that's really stretchy, that can absorb, that's both stretchy and sticky, that can absorb the momentum of that prey and then sort of dissipate that energy. So there's a bunch of different, there's a bunch of work, and I'm super interested in Jeff's stuff on some of this as well. There has been a bunch of work looking at, how stretchy are they, how stiff are they, how strong are they, and which kinds of combinations of silks and spinnerets and structures give you most stretchy and most strong, and all the variations of it, which combinations give you that. You look like you've got a burning question or a big light bulb. Yeah. Just very interesting.
I'll add a quick thing.
Uh-huh.
So in the biomimicry space, of course, people are very excited about silk and emulating that.
Mm-hmm.
And the big aha that came from that was it wasn't just the chemistry. So all the focus was on the molecules, and then they thought, well, if we can just recreate the molecules, we're golden, until they learned that it's the actual spinnerets themselves laying the molecules in a particular form that creates these different properties, and humans have yet to been able to emulate the microstructure of those spinnerets, let alone unpack the full secrets of how they lay out. But that's sort of the next step in, can we emulate spiders?
Yes. Could we create a 3D printer in the form of a spinneret that functions like a spinneret and actually sort of processes stuff? And there's spinnerets, and then there's other structures too. So there's this cool set of, there's a couple of different, like this. So if you're thinking about a web to catch stuff, the strands that are sticky, there's 2 main ways that strands can be sticky. One way is they call cribellate silk. So that's like Velcro sticky. And then the other way is glue sticky. And it's different sets of spiders that use those 2 types of sticky web. And there's a bunch of research right now trying to, that's one of the sort of most argued over parts of the spider evolutionary tree is how many times, cribellums, the things that weave the Velcro silk, how many times those have been lost and had, anyway. But jumping from that. So here's an example of a Velcro style. It's fluffy. This is a strand of silk from the spiral. It's fluffy. It's produced by this cribellum here that's like a plate full of spinnerets. So they're making a swath of silk at the same time. This doesn't do much good without this thing. This is a structure on the hind leg of a spider, and it's a comb that's specifically used to rough up that silk as it comes out. So she's spinning this plate of silk, and as she goes, she's roughing it up with the comb on her hind leg. So all of these things contributing at once, and then you can imagine something that fluffy will stick to anything. If you've been gardening and your hands are all rough and you try to pick up a piece of silk or like a really fine fabric and it sticks, that's the kind of way that this happens to you. It gets so fluffy that it sticks to any roughness in the surrounding environment, hairs on a fly or
So, do we understand why the spider doesn't get stuck on the web?
That's a very good question. A few things we do know. I'm sure there's a ton we don't know, but a few things we do is that some of it is behavioral. The strands, the radii of a web, of a real web in this case, are not sticky. And the spider who made it is very good at mostly holding on to the spaces between the spirals, mostly walking on those radii instead of the sticky parts of the spiral. So that's the behavioral side of it. A physical side of it, the feet of web building spiders are really different from the feet of other spiders. And they've got claws that are oriented in different ways that can help them hold on to stuff without getting stuck to it. So, but I suspect that the feet of a cribbolate of a Velcro sticky spider are different than the feet of a glue sticky spider.
So, right, maybe one gets stuck. Maybe because the Velcro, right, and the...
Yeah. Right. Right, exactly. All right, so here's an example of the one kind. Here's the other kind, and the wheels will look actually oftentimes more similar than this. But this is a glue style of sticky spiral. The radii are going to be very similar, but the spiral is going to be sticky from glue droplets instead of from this structural sticky. And there's been some recent work on this. Some of the stuff suggesting that glue guys have evolved several times from Velcro guys. Has argued that this kind of silk is more expensive to produce than this kind of silk for the same amount of stickiness. So that's might suggest. We'll see, but
By expensive, do you mean from like a
metabolic?
Okay.
Yeah.
I do.
Yeah. So which comes back around to this question of what do you do once you've produced it? Silk is almost entirely protein. So for an animal that's taking its chances at what it catches, it lives only on whatever critter happens to come through the web that it catches. They can't afford to just keep producing all of this protein without getting any of it back. So most spiders that build capture webs eat their capture webs periodically. Some of them eat them every day. And to me, one of the coolest questions in that, and I don't know if anybody has looked at it, is how do they digest it? They'll go and a spider like this guy she'll have built her web either in the morning or in the evening, depending on whether she's a daytime or a nighttime spider. And then at the end of that day or night cycle, she'll take it down and she'll gather it into a ball. As she takes it down, she'll leave the frame up, but she'll gather up all the sticky stuff, and she'll wrap it into a ball, and then she'll eat it and reconsume. So she basically recycles those proteins for use the next day. And what I don't know, and I don't know if it is known, is what enzymes are used, what's the process for recycling that? Because wouldn't it be nice to have such an efficient recycling process that it can happen, basically, at a household scale? Yeah, you got this great product, and whenever you need to, you just recycle it and use it again, have it fresh. Yeah.
Well, and another example or story here is that we shared the glue-based one. It turns out that those droplets, in addition to being like the level of adhesive to capture an insect, they also are charge-based, and so they'll pull any small, really small molecules that are charged out of the air into the droplets. Whether or not that's intentional, right, in that the spider is benefiting from some of those microparticles, and when they're reconsuming, they're getting the nutrients. We shared it for a company that was interested in trapping nanoparticles from flue gas, and how they could, and the particles are small enough that they actually develop a charge as they're moving through the air, and then to be trapped on the silk. Again, just thinking about, who might care and where we might want to keep this information.
Oh, let's see. Yeah.
Is that also a way to sort of introduce contaminants, like human-made pollutants that might be like injurious to spiders? Like, has anyone looked at that?
I don't know whether anybody's looked at harmful stuff that they're ingesting. They've definitely looked at positive stuff, and we probably have no idea on the neutral. So it turns out that for really small spiders, especially really young spiders, it's really hard to catch enough tiny stuff to grow to a bigger size where you can get the bigger stuff. But webs are also catching pollen. Pollen has a lot of protein in it. There's been studies shown that some of the small spiders get a substantial amount of their nutrition during that small, tiny phase of life from eating pollen that got stuck in their webs.
So that answers my question of why they would have it, because pollen is charged in order to ensure that it matches up properly with the plant that's supposed to grow. Right? So there's a charge matching in pollen matching. So pollen has a charge.
So they're not carnivores.
They're omnivores.
Yeah. And people debate whether that's passive omnivore or real omnivore.
Yeah. What does the spinneret look like the glue version? Is it similar to
so I forget which. I'd have to brush up on which spinnerets are doing which. But do you happen to remember which of the spinnerets are doing the glue silk?
The aggregate, glue doesn't. It comes out of an orifice near the spinneret. It's basically so they drop it on. It's next to the flagella, the one where the flagella, which is where it's next to that that comes out.
Which means then they can decide to put it on or not put it on any piece of silk that they want it to be sticky or not sticky, which is an advantage. I had this quote on here just to remind us that when we're interested in features that function in a certain environment or in a certain way, we can look back at both the ecology and the history of the spiders themselves and maybe get guidance from that. That, for example, if we're looking for a glue that works really well in humid environments, we should be looking at the spiders that live in humid environments. And when we're looking for a glue that works in dry environments, we should be looking at them. So so people have done a lot of work looking at the different kinds of silk and what the properties are, and that's a whole pack of literature. It's been fun to just play with, and so anybody who's interested in that can go way deeper. I wanted to give an example of how some other webs are structured, just because they're so cool. So a black widow. So you guys have a black widow up here. I can pass her around. She was in my kitchen, so I decided she didn't get to stay in my kitchen. She can stay in the yard. She can't stay in the kitchen. So she's a gift to the class. A gift to the Biomimicry Center. Black widows have a really cool, their webs look disorganized, but they actually have a lot of structure to them, including this cool thing so they've got this sheet web kind of structure that they're hanging out in, and you can see you can turn it any different way, and she's comfortable. She's holding on to enough pieces around her that she's comfortable any way you do it. So she's in the sheet web. They also do these this sort of capture function where they take, imagine that the sheet web is the ceiling, and the spiders will they'll drop a line from the sheet web, and they'll stick it to the ground, but they will stick it sort of lightly stuck, gently sort of attached to the ground, and then they'll put glue on the bottom inch or so, and they'll tighten it. They'll put it under tension. So when let's say a cricket comes blundering along, minding his own business, and walks into this, it gets stuck to the glue. It struggles. Its little bit of struggle is enough to pop the attachment loose from the ground, and the tension on the string flings them up into the web.
I didn't watch the video now.
Yeah, it's pretty darn cool. So imagine that except you're walking under some pretty great flings it up into the web, where she can then dash out and throw silk around his legs and immobilize him for lunch later.
So, I mean, think about the ability to determine how much tension is necessary, right? So, because you've got your whole sheet web on one end, and if you put too much tension, you're pulling your sheet web down. And yet you've got to have a little bit of glue that can maintain that tension, but then enough breakage. I mean, talk about the mathematics, right, if you will, and the sensors that she must have in order to say enough tension, not enough tension.
Yeah. Sensory systems of spiders are off the charts cool. They've got sensors for every possible function. They've got chemosensors, tactile sensors, vibration sensors, eyes. They've got
far more sensitive than any of our sensors.
Yeah. So if we're designing sensors for stuff, also look to these guys and to the other arachnids. There's some really cool weird sensors on. There's a lot of stuff that we don't even know what it functions for. But you know, if it's on an animal, it's probably doing something. So, yeah, that's cool. All right. And this is probably how she also gets like dangerous things like scorpions flung up into the web where they're not so much of a threat to her. So, all right, just one little plug there that again for there being a lot known about silks, and it feels to me like the integration between the materials folks and the biologists has been getting better, and that's been really useful. So, but there's still a lot. There's a lot more I think that we can get from having more of that integration. So, all right. So for the group that went off the web, there's all sorts of crazy diversity. There's actually some thought that diversification rates, speciation rates, accelerated in the group that went off web. So I'm gonna tell you guys a little bit more about jumping spiders, eyes, and then we'll move to looking at some of them. These guys, they come in bright colors, and they do a lot of interesting behaviors that we can see. So to me, that says right away that they must be able to see the stuff that they're doing, right? Why would they have big, bright colors and fancy dances if they didn't also have really good eyesight? And you can just watch them chase down and pounce on things, and you can tell that their eyesight is really good. So how does that happen, and how good is it? So there's been some cool work done on sort of spatial acuity, so detail vision, and it turns out that it's been documented now jumping spiders have better detailed vision for their size than any other creature ever found. So these guys, falcons are comparable. We're not nearly as good. So super vision. How do they get it? What goes into having amazing vision at a tiny size? These guys are, most jumping spiders are less than half a centimeter long. So how can you get that great a vision with? So for one thing, they've got 8 eyes, right? Most spiders have 8 eyes. A few of them have only 6. And each pair of eyes has a slightly different function. So these guys are telephoto eyes. These guys are sort of wide-angle eyes. These guys are telephoto, wide-angle, but still sees a lot of shapes. Motion detecting. And then these ones are, on some of them seem to be vestigial and others seem to be functional. But anytime you see something and you can't figure out the function, don't assume it doesn't have one. Look at it. So I'm going to show a little bit more about these front eyes because they call them anterior median eyes. The front eyes of jumping spiders are incredibly evolved as the optics are pretty amazing. So I'll go into that just for a few minutes. So basically, anytime a jumping spider is interested in something, anytime something catches their attention, you'll see them pivot and look at it, right? So that's one of the ways that as you're cruising around your daily life, you'll notice a jumping spider because you'll see out of the corner of your own eye, you'll see a pivot behavior. And when you see that, like that, you should look. And a lot of times it's going to be a jumping spider who's decided they're going to look at you, right? So it's that putting those front eyes right on something. They also have, they have muscles. So they have these long conical retina that go way back into the head. And they have muscles on those. The fronts of the eyes are secure to the carapace. They can't move. They're part of the exoskeleton. They're part of the mass, right? But the back of the eyeball moves all over the place from muscles. And this is a Lissomanes, and I have a couple of them up there. You can tell if they're looking at you, if an eye is looking at you, because the retina back here is dark, and the sides of it, so the photoreceptors are look dark, and the sides are kind of reflective. So if an eye is looking straight at you, it's going to be dark. So that's that. That eye is looking straight at you. And that eye is looking somewhere else, and you're seeing the side of this cone instead of the back of the cone. So it's super creepy and super cool, and see it up here. And some of you guys saw it last night. It's like weird. All right, the lenses have a telephoto component to it, a diverging lens that magnifies the image. It's got a 4-layer retina that each layer is sort of tuned to different wavelengths. They've got all the way from ultraviolet to red. And then they've got all sorts of weird, all the way down to the fine structural scale of the photopigments themselves and the rhabdomeres. Like every single piece of these eyes has some cool, weird complexity. And if you want to dive in more, I have a couple great papers on some things. So basically, super, super good eyes. And then in these itsy bitsy spiders, you think, well, how does a brain that size process and make use of and make sense of this immense amount of detailed information coming in? And that's, I think, we're still on the frontiers of understanding that. How does a tiny, tiny, tiny brain process that much information? I can see that could be maybe really useful for other sensors. I would love it if my camera both had an eye that was that small and could actually distinguish features. We don't really know how they do it, but we can tell from behavioral work that they do it, that they are differentiating between different kinds of prey. They're differentiating between a handsome mate and a not so handsome mate, a really good dancer and a okay dancer. They're making all of these differentiations, and they're using that information to do crazy things like, chart a path around a dangerous prey. So this one here is called Portia. She's kind of the poster child of really, really, really smart spiders. And so a lot of behavioral research has been done on her to look at and shown that when she's attacking something that doesn't pose a threat, like a fly, she'll go straight at it and just pounce on it and bite it, and eat it. If she's attacking something that is dangerous, like another spider, she'll chart a path all the way around to behind it. And she can do this thing that toddlers can't do, which is lose sight of something and remember what they're doing. So that's sort of a hallmark of advanced brains in the neurobiology research, is to like lose sight of something and still remember that it exists. So these guys, yeah, have been done. Been shown with them. So that's all on this part, and let's look at some stuff. Yeah, and talk about stuff. Cool. So we've got we passed around the black widow. I've got here a couple different jumping spiders. This one's a Habernatus, and it's one of the ones it's around here, and it's a group with about 75 species, and each one of them has fancy dances that have both visual components and auditory components. And you can look up you can find some videos of some of the great dances they do. And we've got some of these Lissomanes. How are you guys? Oh, you're still here. Good. These guys that are so translucent that you can see their eyeballs through the tops of their heads. You can see them looking at you. So, yeah, we've got a couple other things. And we've got books, so come on up. And those of you guys who saw stuff yesterday can help each other find stuff. Find those eyes and look at stuff. And yeah, and then we can talk about all the rest of it too. And if anybody wants pictures of more stuff that's right around them, I've got more. But mostly I just want to encourage people to look at stuff, to pay attention, and to ask questions and to say, what the heck are you doing when you see a cool spider? Because there's we can find right around here examples of most of the major branches of spider evolution exist in Arizona and probably even on the block. Yeah, and if you guys want to look at other stuff in the book too, she's got good examples of things like feet. Somebody else, you ask, how do they not get stuck? Well, there are some spider feet that are really good at getting stuck. Oh, so there's a third kind of jumping spider up there in a little tube, and they're ones that I have seen hunting upside down. I watched one walk across my ceiling upside down, and at first I didn't know what it was doing, but it was obviously stalking something. They look like little cats when they start to stalk stuff. And it turned out there was a lacewing on the ceiling by the light. The spider comes up, she sort of creeps up to about 2 inches away from the lacewing. It's all happening upside down. She pounced on it upside down. She took a flying leap. She defied gravity. I still don't understand how she did it. She jumped and swung herself to catch the thing upside down, and I still don't understand how she did that. What are the mechanics behind being able to pounce upside down? Yeah.
Well, I wonder, because I've heard that for like bees, flying is like flying through honey. It's like swimming through honey because of the viscosity and their size. And so I wonder if for her the air is much thicker, you know?
It could be,
but still.
It's still, yeah.
She must have had a tether.
She has a tether. So that's one of the cool things one of the main uses of silk is drag lines. So that, spiders have their spinnerets on the tips of their abdomens. Almost all spiders, almost all the time, when they're just moving around, they're leaking a little strand of silk. But with jumping spiders, it's very intentional. When they're about to jump, they will actually attach that drag line to the surface, and then when they leap, they use it as a bungee cord plan B, like a safety harness. If they jump and they miss and they fall, they can climb back up it. But they also use it. So you can see it in this picture where she's leaping, and you can see actually a double drag line behind. Jumping spiders use drag lines to help control their jump, so that they land exactly where they meant to land. And once in a while you'll see a drag line break in mid jump, and they'll go tumbling head over heels. So you can tell by what happens when you have a failure that it's providing that major stability and and that it's a major tool in getting where they want to be. So on the upside down, I can't even quite get my head around the mechanics of how you, even with a tether, how you swing up to catch something. But yeah. So if somebody wants to do high-speed videography and test that, that would be cool. I would love to know the mechanics of how you do that.
I bet you could get funding for that one,
Yeah.
right? Who wouldn't want to figure out doing
Yeah.
that?
Sure, the military would want to know.
Right? And the movie industry. The movie industry probably really wants to know that. We can make Spider-Man do it. Figure this out.
I had a couple
Yeah, I should
It was just one of those things where window here, sunlight here.